The transmission is what changes the torque and speed of the engine so that the motive power, which has undergone primary speed reduction, is appropriate to the current driving conditions. Let's look at how the transmission works using computer graphics to simulate the operation. You know that starting the engine and climbing uphill both require a high level of power. In situations like these, the number of teeth on gear A on the drive side is reduced, and the number of teeth on gear B on the driven side is increased. You can see that gear B is rotating at a slower speed than gear A. Let's talk here about why changing the number of teeth on the gears changes the torque. When the gear is rotating, because to every action there is an equal and opposite reaction, for a force acting at the contact point, there will be an equal and opposite force F. At this point, if we use a wrench and turn the bolts at the centers of the gears, assuming the torque is being applied, we can express the rotational torque TA of gear A as an equation showing that a force F is applied at the contact point of the radius RA of the gear. In the same way, the torque TB of gear B can be expressed using an equation like that shown here, with the radius of gear B being twice as large as that of gear A. Therefore, when the number of teeth on gear B is twice that on gear A, the level of torque is twice as high. Conversely, at high speeds, when we do not need a large amount of torque and the rotation speed of the drive wheels is increased, we increase the number of teeth on gear A on the drive side and reduce the number of teeth on gear B on the driven side. You can see that gear B is now rotating faster than gear A. In this way, by changing the speed at which gear A and gear B rotate, or in other words, by changing the number of teeth on the gears, we can produce a torque and speed that are appropriate to the driving conditions. The ratio of the speed of gear A to that of gear B, in this case, is called the gear ratio. If the torque is doubled, the speed is reduced by half, and the amount of work produced per minute, namely the horsepower, remains the same. In an actual transmission, there are a number of stages provided between the gear which affords the maximum climbing power and the gear which provides the maximum speed. This way, the appropriate gear ratio for the current driving conditions can be selected. The transmission system is made up of the counter shaft, which served as the input axis, the drive shaft, which acts as an output axis, the various gears which convey the drive power to the engine, and the gear shifting cam and gear shifting fork, which are used to operate the gears. This type of transmission is called a constant mesh transmission, because the gears on the counter shaft are meshed with the gears on the drive shaft right from the start, and remain meshed, rotating together. At any given time, however, either the counter shaft gear or the various gears on the drive shaft are not coupled to the shaft. In neutral gear, therefore, the power from the counter shaft is not transmitted to the drive shaft. Let's look at how power is transmitted when we shift from neutral into low gear. In neutral gear, the low gear of the counter shaft is consolidated with the shaft to form a single unit. But the low gear of the drive shaft is free. When the gear shifting lever is operated, the gear shifting cam rotates, and the gear shifting fork slides to the dog, so that the dog is fitted onto the low gear of the drive shaft. Because the dog is coupled with the drive shaft, power is transmitted from the counter shaft to the drive shaft. As the rider shifts through various gears from low to top gear, the gear shifting cam and gear shifting fork work together to change from one speed to the next. There is also a type of automatic transmission which uses a V-belt. This gear-changing mechanism consists of a drive pulley, a driven pulley, a drive belt, and a centrifugal clutch built into the driven pulley. The drive pulley is attached directly to the crankshaft and changes the width of the pulley in response to conditions such as throttle operation. This changes the position of the drive belt, which automatically changes the reduction ratio. This system allows smooth increases and decreases in the motorcycle speed and drive force. The weight roller moves as centrifugal force acts on it, and in turn causes the drive pulley to move. When the centrifugal force pushes the weight roller outwards, the roller presses on the movable drive face, decreasing the pulley width. The drive belt is pushed upwards, increasing the belt diameter, so that the reduction ratio is reduced automatically. The driven pulley is generally pushed by a spring in the direction in which the pulley width is narrow. When the diameter of the belt on the drive pulley side is increased, however, because the belt length is constant, the spring of the driven pulley is defeated by the drive pulley force, and the driven pulley diameter becomes smaller. At this point, the power being transmitted from the engine by the belt is conveyed from the clutch drum to the drive shaft by the centrifugal clutch built into the driven pulley. The final reduction system is the device which conveys power from the transmission to the drive wheel. The system you see here, where the rear wheel is driven by means of a chain, is called a chain drive system. In the chain drive system, the gear ratio is determined by the number of teeth on the engine sprocket attached on the transmission side and the rear sprocket attached on the wheel side. Also, on an ordinary motorcycle, a damper is installed between the rear sprocket and the hub to absorb shock produced by changes in torque. This is designed to boost riding comfort and to assure the durability of the drive chain. A system in which the rear wheel is driven by means of a shaft rather than a chain is called a shaft drive system. The reduction ratio in the shaft drive system is determined by the ratio of the number of teeth on the secondary gearbox attached on the engine side and the final gearbox attached on the drive wheel side. The shock produced by changes in torque is absorbed by a damper attached on the drive shaft. When the damper on the engine side and the damper lifter on the drive wheel side are turned, the spring is compressed, acting as a shock absorber. Like the chain drive system, this is designed to boost riding comfort. In this way, the power from the engine is conveyed at the appropriate ratio to the drive wheel. Let's look one more time at the path followed by this power. First of all, the size of the engine torque is determined based on the force F produced by the combustion pressure and the length L of the crank arm. This engine torque is increased by the primary reduction system, but the speed conversely drops so that the desired gear change is carried out by the transmission through the clutch. The power is reduced further by the final reduction system and is conveyed to the drive wheel. The reduction system from the starting point until the drive power reaches the wheels is called the overall reduction ratio. It is expressed by multiplying the primary reduction ratio by the transmission and final reduction ratio. In this part of our series, we have covered the carburetor, which turns the fuel-air mixture sent to the engine into spray form, and the transmission system, which conveys the drive power produced by the engine to the drive wheel. We hope that through this video you have gained a better understanding of the basic systems that make up a motorcycle, and that you will be able to put this knowledge to use effectively in your everyday work.